Hello everyone. An unbalanced force on a rotating member of a machine component, for example a rotor or a component like a gas turbine, would result into vibrations, which vibrations can lead into catastrophic failures of the machine, as well as noise and discomfort. Therefore, an engineer must work so hard to ensure that unbalanced force is put out of action by either adding another mass to counterbalance that other unbalanced mass, or by drilling a hole on a machine component that is rotating to counterbalance the effect of the other inertial or centrifugal forces that are bringing an unbalance in that machine component. In this video, we are going to look at a scenario that requires us to determine the total unbalanced force on a machine component, and also determining the position of a mass or a hole that can be drilled to make sure that rotating member is balanced. A cast steel rotor 40 mm thick that has 4 holes drilled at radii of 50 mm, 100 mm, 125 mm, and 150 mm respectively. The holes are 25 mm in diameter and located as shown below. Then analytically determine the magnitude of the total unbalanced force on the spindle bearings that are rotating at a speed of 720 revolutions per minute, and also we are required to determine the location of a 12 mm diameter hole that can be drilled for balance, taking density of steel at 7.8 megagrams per cubic meter. This is the steel rotor that has got holes at A, B, C, and D. Remember, these holes have been put or drilled by removing some particular mass. So therefore, the mass that we are going to consider are those masses that would have occupied these positions where the holes are, because they are the ones responsible for balancing or unbalancing this particular rotating member. The radii of rotation, hole A is at 50 millimeters from the radius of rotation. Likewise, B is at 150 millimeters, C is at 125 millimeters, and D is at 100 millimeters from the axis of rotation. And the angles, the respective angles, are also indicated on this particular diagram. Let's go to determine the solutions for this particular problem. Now, the diameter of each hole is 25 meters out of 1,000. Thickness is 40 millimeters or 40 out of 1,000 meters. Therefore, remember, since we are looking at the unbalanced force, this is a centrifugal force that is a product of mass and the square of angular velocity and radius of rotation. Then it means for us to determine the mass of the amount of steel that has been removed to create that particular hole, then we need to determine the volume. Then multiply it by density, we shall get the mass. So volume of one hole is equal to pi d squared t, or pi d squared, which is the cross out of 4, which is the cross section area, times the thickness. We will be able to get the volume. Then it is going to be pi out of 4 times 25 out of 1,000 squared, then times 40 divided by 1,000. Our volume is going to be 1.9635 times 10 power negative 5 meters cubed. Therefore, mass is going to be density times volume. Density is 7.8 times 10 power 6 grams. So converting it to kilograms, I will divide it by 1,000. Then I multiply the density by 1.9635 times 10 power negative 5, which is the volume, and my mass, or the mass of that material removed from the hole, is going to equal to 0.1532 kilograms, or 153.2 grams. Therefore, if I analyze this system as a system containing masses at different radii from the axis of rotation, then I would also indicate their respective angles from a particular reference plane. So if I consider A as a reference plane, then it means B is going to be at an angle 75 degrees from A, C is going to be at an angle of 165 degrees from A, and D is going to be at an angle to 70 degrees from A. Now, if I consider equilibrium of this system, then the sum of vertical forces as a result of centrifugal forces acting on these masses, remember I have a centrifugal force acting radially, Now the sum of vertical forces, since they are at a particular angle, the sum of vertical forces would be m1 r1 sine theta 1 plus m2 r2 sine theta 2 up to m4 r4 sine theta 4. Of course, I would have multiplied by the square of angular velocity, but remember, since it is a constant, then it is multiplied this way and multiplied this way, then it can be cancelled out, so that I remain with the m1 r1 sine theta of that angle at that position. Then let that one be equation 1. Then equation 2 would be consideration of horizontal forces. The resultant horizontal force would be the sum of the resultant the horizontal forces, which would be m1 r1 cos theta 1 plus m2 r2 cos theta 2 up to m4 r3 cos theta 4, so that I be able to get the resultant horizontal force. Of course, I would also multiply by square of omega here, square of omega here, but it would be cancelled out, and that is equation 2. Now, if I substitute in the values that are given, the values given for mass, since the mass of each hole is a constant, I will put it out, and let me consider it in grams. So 153.2 into 50 millimeters sine 0. The angle A makes with the horizontal is 0, therefore I will say it is sine 0 plus 150 sine 75 plus 125 sine 165 plus 100 sine 270, and this would give me a value that is equivalent to 11833.36 grams millimeter, which is the same as 0.118334 kilograms meters. Likewise, if I substitute in the values to calculate the resultant horizontal force, it would give me 0.00488898 kilograms meters. So having gotten the resultant vertical and horizontal forces, then I can calculate the out of balance force, or the resultant force of that system, which will be the square of the sum of vertical forces and plus the square of sum of horizontal forces, everything under root. So if I substitute in those values as given above, I would get a value equivalent to 0.12803 kilogram meters. Therefore, this force would equal to mass times the radius times omega squared. Remember, what I have here is a product of mass and the radii from the axis of rotation. Then I should multiply it by omega squared, since I had neglected it from above. And the omega squared is given as 720 revolutions per minute. So converting it to radians per second, it would be 12 times 2 pi radians per second. So I square it and multiply it by what I have gotten above as the product of mass and R, which is of the resultant out of balance force. This force is going to equal to 72.77 newtons, and if I use an approximation of the above value, I would have 0.013 times 24 pi squared, and this would approximate 0.74 newtons, which is approximately equal to what I have above. But of course you should always avoid over rounding off, because you lose accuracy. So you need to keep at least 4 decimal places. Now we are given that if a hole of 12 millimeter diameter is drilled, we are required to determine its location and therefore the position, of course, of the balance force. That this hole has been drilled to make the system balanced. So we need to determine the mass of the material removed for us to get the 12 millimeter hole. That mass is going to be density times volume, whereby volume is now pi out of 4 times diameter squared, which is now 12 out of 1,000 I square, times the thickness, which is a constant as 40 millimeters, and converting it to meters would be 40 divided by 1,000, then times the density, which is 7.8 times 10 to the power 6, that is grams, so converting it to kilograms, it would be 7.8 times 10 to the power 6 divided by 1,000, then that would be kilograms, then per cubic meter. So this is what I would get if I substitute in those values, and then the final mass would be 0.0352 kilograms. That is the mass of the material removed to create a hole of 12 millimeters. Therefore, the inertial force due to this mass would be m prime r prime, and r prime is the radius at which it is going to be put from the axis of rotation. And this force, if we calculate it, it is going to be equal in magnitude to the out of balance force, since it is meant to balance the other out of balance force on the system. Therefore, I know that this m mass times the radius for the out of balance force is 0.0128. So it is equivalent to this mass times its radius of rotation, of course, from the axis of rotation, and therefore it would be 0.03529 times r prime. So we need to get that radius, and it is going to equal to 0.0128 out of 0.03529, and this would give us 0.363 meters, which is approximately equal to 363 millimeters. Now that unbalanced force, we have to determine its position. If we determine its position, it can help us to also locate the balanced force now. Since the two forces, the unbalanced and the balanced force, are equal in magnitude, but we will find that they will be equal in magnitude but acting in different senses. Therefore, to determine where the unbalanced force acts, I will take tan theta of sum of the vertical forces out of sum of the horizontal forces, and this will be theta equal to arctan of negative 2.42, and this will give us negative 67.5 degrees. So I will come to my diagram and draw. This is the direction of axis, then negative 67.5 on when I'm to indicate it on a diagram. Then I would go to A. Of course, A is horizontal, so I go to A, then I move in a clockwise direction, because clockwise angles measured in a clockwise direction are negative, whereas those measured in anti-clockwise direction are positive. So that 67.5, I put it in the negative, in a clockwise direction from A, then I will get the position where the unbalanced force acts. So this is the unbalanced force. That means the balanced force, or the force that balances the system, is going to be equal in magnitude, but is going to be in an opposite sense to this unbalanced force. Therefore, it will act along this similar line, but now we need to determine the angle with which it makes from the horizontal. Then I will move my arrow from A in a clockwise direction. I will measure this angle, and this angle is going to be 180 minus 67.5, which gives us 112. This is going to be 112.5 degrees. Or if I measured it in a clockwise direction, then it would be 360 minus 112.5, and this would be 247.5 clockwise of body or mass A or hole A. Therefore, the balanced force is at 112.5 degrees counterclockwise of A, or 247.5 degrees clockwise of A. Thank you so much.